welcome back. The next unit in the course that we're going to take a look at is derivatives. Before we get into what derivatives are, let's take a moment though to refresh our memory on a few key concepts that we're going to need from advanced functions. The first concept that we're going to be interested in is the average rate of change, and the second, we're going to talk about the instantaneous rate of change. So recall from advanced functions that the average rate of change graphically can be described as a secant between 2 points. If we have 2 points, say x and h1, and we connect these 2 points, the rate of change between these 2 points will be the slope of this curve. Whereas if you remember the instantaneous rate of change, we associated with the slope of this tangent. If you remember from advanced functions, we covered both of these concepts in a fair amount of detail. However, instantaneous rates of change, we only learned how to approximate. Throughout the process of this course, we will learn how to find these exactly, which brings us to the definition of derivatives. So we're going to look at our first principles definition, which this is actually a fancier form of the slope formula that we learned in grade 9. We see that our numerator here is f of x plus h minus f of x all over h. Well, let's take a look at what these two things are on our graph. Well, if we have f of x plus h, that would be this point here plugged in to the function f of x, which is this y value. If we look at f of x, that would be just the value of x here plugged into the function, which would give us this y value. Well, what about this h? H would be the distance between x and h1, which would be our delta x. So you can see here that this is actually the same formula that we're used to when determining slopes, which should fit our intuition. As we said, rates of change we describe via slopes. The one exception here is we've added the limit here. Notice that if we draw this first secant here, it doesn't do a very good job of approximating this tangent. How could we do better? Well, we know that if we slide this point closer to x, we could draw a new secant here. And notice that these two lines get closer together. Each time we slide this point h closer and closer to x, the line or the secant created becomes closer and closer to the tangent. If we could make this point h 0, or right on top of x, then we would end up with this tangent line, and we would find the slope exactly. Algebraically, we know, however, if h equals 0, then this fraction would be undefined. So we apply the limit here to try and figure out what happens as h gets really close to 0. So let's take a look at an example to figure out how we can handle this problem. So let's take a look at the function y equals x squared again. If we apply the formula here, f of x plus h minus f of x, and we plug in for x squared here, we'll get x plus h squared, that's our f of x plus h part, and then f of x unmodified here, so just the x squared, all over h. So let's just follow this through algebraically. We can expand this binomial to yield this expression, x squared plus 2xh plus h squared minus x squared, and we can get a bit of cancellation here. X squareds cancel out. We can then factor this expression and then cancel out the h's in the denominator. This will be our general strategy when solving these first principle problems in general, is we always want to try and cancel out this h in the denominator. Why? As we saw in previous examples, once there's no longer an algebraic problem caused by h going to 0, we can actually allow h to go to 0. So we plug in 0 for h, and we're left with the function f prime of x equals 2x. Now I've just introduced a new form of notation here, f prime of x. Well, all this means is, when you see a prime, that denotes the derivative of a function. So the derivative of x squared is f prime, which is 2x. Now I have written two different forms of notation here. One of them is Newton's notation, this f prime of x form. And typically we'll use this form to denote the derivative anytime we're given a function in terms of f of x. And if we were given a function in terms of y, we can use dy by dx, which means the same thing. This means the derivative of y with respect to x. Now what can we use this for? We've figured out that the derivative of x squared is 2x. Well, that's not very helpful, but what we can do with this is if we want to know the slope of a tangent at a specific point, so say x equals 3, we can plug 3 into our derivative function and it will return the slope at that specific point. We saw in our previous example how to use and apply the first principles formula. But as many of you may already be thinking, that looks like a tedious and difficult way of finding derivatives. Fortunately, we actually have a better way of going about this. Once we establish some base rules of how derivatives of functions behave, we can use some general rules to make this quicker and easier. So we're gonna accumulate a number of these rules throughout the course, and the first two we can add to our list are these two. So the first one we'll call our power rule. So the derivative of any function that's of the form x to the n will have the derivative n, so bringing down the exponent and multiplying it by the function, to x to the power of n minus 1. So if this was x squared like we saw in our last example, n would be 2, and n minus 1 would be 1, and we'd have 2x. I've introduced this new piece of notation, d by dx. What this means is this is the derivative operator. This means take the derivative of the following function. The next rule we can add to our list is the derivative rule for constants. If we're taking d by dx of any constant c, so this can be any finite number, the derivative will be 0. This will be useful to know. Next, let's apply these rules in figuring out what will happen when we take the derivatives of combinations of functions. So similarly with limits, let's explore what happens when we take the derivatives of products, quotients, and compositions. So if we're given f of x times g of x, and we want to find the derivative of it, unfortunately it's not going to be as simple as take the derivative of f of x and multiply it by the derivative of g of x. We end up with a more complicated expression. How we read this expression is the derivative of the product will be f prime of x times g of x plus f of x times g prime of x. So what does this mean? It means that if we take the derivative of f of x and multiply it by g of x unmodified, and add it to f of x unmodified times the derivative of g of x, then we'll end up with an expression for the derivative of these two. Similarly, we can come up with an expression for the derivative of quotients. If we have f of x divided by g of x, the formula will be similar. We take the derivative of f of x, multiply it by g of x unmodified, subtracted by f of x unmodified times g prime of x. And we divide that all by g of x unmodified squared. The final useful formula that we're going to make use of is the chain rule. So if we have a composition of functions, f of x of g of x, the derivative for this will be a little trickier, but we'll see an example to make it clear. What we're going to do is we're going to take the derivative of f of x and evaluate it, or plug in g of x unmodified, times the derivative of g of x. So let's take a look at some examples here. Our first example will be how to apply the product rule. In this case, we have x times x minus 1. So we can imagine that f of x is the function x, and g of x is the function x minus 1. Well, if we apply our power rule to the function x, we'll get the derivative is 1. And plugging into our product formula, we'll say 1 times g of x unmodified plus f of x unmodified times the derivative of g of x. And if we take the derivative of this, the derivative of x is 1, and the derivative of 1 is 0. So we're left with the total derivative being 1. Following through our algebra, we can simplify this to 2x minus 1. Similarly, we can apply our quotient rule. If we're given a function that looks like this, the derivative of 1 over x, well, in this case, let's apply our formula here. Well, our formula says let's take a derivative of the numerator. Well, our numerator is 1, and according to our derivative rule for constants, the derivative is 0 times g of x, or the denominator, unmodified. We get x minus the numerator, which is just 1, times the derivative of the denominator, which again is just x, and applying our derivative rule, we get 1. So following through the algebra, we end up with minus 1 over x squared. And in the final example, which is perhaps the most tricky example, we're given a function here, taking the derivative of 2x plus 1 all squared. Well, first, let's take a look. How can we separate this to look like this, f of x of g of x? Well, our outer function looks kind of like x squared. Our inner function looks like 2x plus 1. So let's just go ahead and apply this formula. Well, the derivative of the outer function is just 2x, so 2 times whatever was inside, which is g of x, 2x plus 1, times the derivative of the inner function. And if we take the derivative of this function, we get just 2. Simplifying, we're left with this. Hopefully this is clear. We'll take a look at a lot of these examples in your homework. Good luck.